This PowerPoint is over graphical analysis of motion. So basically we're going to be looking at graphs for motion, that's velocity versus time, position versus time, and acceleration versus time graphs, and describing the motion based on those graphs. All right, so we know that the position versus time graph, if we take the derivative, we get the velocity versus time graph, and for velocity versus time graph, to take the derivative, you get acceleration versus time with that. And then when we take the acceleration versus time graph and we take the integral, then we get the velocity, actually change in velocity. So we get a velocity versus time from that. And then from the velocity versus time, we take the integral, we get a position versus time. So essentially we've got the calculus that takes us from position versus time to the velocity, velocity to acceleration. Then we got the integrals that take it from acceleration back to velocity and then back to position. So in this example, we have a position versus time graph where the slope is positive. Okay, so describing this motion, we see that we start from an initial position of 0 and we increase our position. So we move in the positive direction. The slope also indicates that we move in the positive direction. The slope of this also indicates that we have a velocity. So positive velocity moving in the positive direction starting from 0. The second graph says that we start with a positive position, so that positive position, but we are actually moving in the negative direction. So we have a negative slope, so that means a negative velocity. Even though we have a positive position the whole time, our position is decreasing, getting closer to 0. So therefore we have a negative displacement. C, we start with an initial position that is negative, but then we move away from 0, so we have a negative negative velocity. So that slope indicates velocity, and negative position, we're moving further away from the origin. And then this last example, we start away from the origin in the negative direction, but we're moving in the positive direction as we keep going. So the positive velocity indicates that we're moving in a positive direction. We'll have a positive displacement, even though the position is negative the whole time. For a velocity versus time graph, this example says that we start with a positive velocity, but we have a constant velocity the whole time. Now that means we're still moving, we're going somewhere, but we have the same velocity the whole time. The second example, we have a negative velocity. You'll notice the velocity here is less than the velocity there. So the amount of velocity, what we call the speed. So we have a negative velocity, just meaning we're moving in the negative direction, but it is also constant with a slope of 0, meaning acceleration is going to be 0. Our next example, we're going to start with a positive velocity, but then we're going to decrease our velocity. So that means we have a negative acceleration. So for this part right here, the beginning to 0, we decrease our velocity and we're going to move from a positive velocity to 0, which means we're going to slow down. But you'll notice at 0, we go to the other side, which means we now have a negative velocity, and then we keep increasing in the negative direction. Now, I know this looks like it's decreasing, and indeed it is, according to the graph, but that also means our speed is speeding up because our negative velocity with a negative acceleration, remember the slope indicates acceleration, negative velocity with a negative acceleration means we're speeding up, but we're speeding up in the negative direction. Then the next example, we start with a negative velocity, but we have a positive acceleration because we've got a positive slope. So that means we're actually going to be slowing down. You can see that the velocity is getting closer and closer and actually hits 0 at this point. So remember that the positive or negative slope for a velocity versus time graph doesn't indicate whether you're speeding up or slowing down. But if you have a positive velocity with a positive acceleration or a negative velocity with a negative acceleration, you're going to speed up. A positive velocity with negative acceleration or a negative velocity with a positive acceleration, you're going to slow down. All right, so in this example, we have an object that's moving to the right. You can see that we start with an initial position of 0. We start with an initial velocity of 0, and then it goes all the way to the end here. All right, so what is our position versus time graph, our velocity versus time graph, and acceleration versus time graph? So let's start with our position. We start with a positive or with 0 position, and we move in the positive direction. So we're going to stay above the x-axis, and then we're speeding up, which means the slope of that position versus time graph is increasing. So as we start with 0 velocity, we start increasing our position and we increase the slope. So that gives us a parabola that looks like this. For a velocity versus time, we start with 0 velocity, but we have a constant acceleration as we go down the ramp. So that means we move in the positive direction. So we have a positive velocity with a positive direction. And then the slope of this graph indicates that we have a positive acceleration. That acceleration is going to be constant. So we got a positive constant acceleration for the acceleration versus time graph. In this next example, we start over here with this initial velocity of 0, but the position is going to be positive. But notice as we go, we are going to be moving in the negative direction. So that means our position gets closer and closer to 0. So we start with a positive position, but then get closer to 0. So our position versus time graph is going to start with a positive value, but it's going to get closer to 0, and it's going to speed up, which means the slope is going to increase. Now notice the slope, the velocity is in the negative direction. So the slope is going to increase in the negative direction, and that means it's going to be an upside down parabola where the amount of slope is going to be increasing, so it gets more and more negative slope for that. For the velocity versus time, we're going to start with 0 velocity because that's what it says here, but then we move in the negative direction, so that's why we have a negative increase in velocity in the negative direction. And since we're speeding up, then we have a velocity and an acceleration in the same direction, so the slope of the velocity versus time tells us that we have an acceleration that's going to be negative. You'll notice here if you look at the slope at any point on the position versus time, as it increases, the value increases in the negative direction, just like the slope increases in the negative direction. For this example, we start with an initial position of 0, initial velocity of 0 as we're going up the ramp, then we stop at the top. And as we stop, we come back down to the initial position. So what does the position versus time graph, velocity versus time, and acceleration look like? Well, as we're moving up, our position is increasing, but then it stops and comes back to 0. So we're going to start at 0, and since we have a constant acceleration, this is going to look like a parabola. So you go up and then back down. So we have this parabola starting from 0. The velocity is decreasing, so the slope is getting less. And so we have 0 slope at the top, and then the slope is increasing as we come back down. The velocity versus time, we have a positive velocity, but then we have a negative acceleration, slowing it down. And then when we get to the top, we speed up as we come back down with our acceleration being negative. So we got a negative acceleration the whole time. In this example, we're going to start at the top, and as we start at the top, we're going to accelerate down, but then this part right here, we're going to move at a constant speed. We're going to assume there's a constant transition here. So our position versus time graph is going to be increasing in the positive direction because we're speeding up, but at this point right here, we have a transition where we have a constant velocity, so we have a constant slope for this point. And that dashed line basically represents that transition between the two. Now the velocity versus time is increasing, but then at that part right there that's level, it has a constant velocity. So our acceleration is going to be a constant acceleration until we get to that transition right there where we have 0 acceleration, since we have no change in velocity in that part. So in this problem, we start with a block that is at the top of this ramp. And as it's at the top of the ramp, we're going down a frictionless track. So with no friction, we have no outside net force, only gravity is going to be pulling it down. So we sketch the motion of a position versus time, velocity versus time, and acceleration versus time. So notice that the position is over here at 0. So we start with a positive position, but we start with 0 velocity. Now, as we come down here, we're actually coming towards the position of 0. We're coming towards the origin. So we have a negative displacement as we're moving this direction. So we have an increase in velocity as we come down this ramp, but it's increasing in the negative direction. And then we have a slope, or a part here where the velocity is going to be 0. It's going to be a constant velocity with no acceleration. Then we come back up this ramp here, and as we come back up the ramp, we're going to slow down. So if we look at the position versus time, we see that we start with some position, but then we speed up, so the slope gets more negative. And then this part right here where we transition to the constant velocity, we have a constant slope, and then we slow down as we come up, so we have a parabola that's pointed upward. All right, our velocity versus time is going to be increasing in the negative direction. So we're going to be below the x-axis, and then we're going to have a constant velocity. Then we're going to be decreasing in the negative direction. All right, so our velocity versus time is going to be increasing in the negative direction, then it's constant slope. And you'll notice the second part here, it's a steeper slope, and the reason it's steeper is because this incline is steeper, so that means more acceleration. So our acceleration versus time, we have a negative acceleration, and then as we slow down in this part right here, we have a positive acceleration. And notice because of that steeper slope, for the velocity versus time, we're going to have more acceleration for that part. All right, so given our position versus time, we want to look at the velocity versus time. Our position versus time has a constant slope constant slope, and constant slope. So that's a positive slope, 0, and then negative slope. So our velocity versus time graph will be a positive velocity, and then 0 velocity, and then a negative velocity. You'll notice the negative velocity is going to be more than the positive velocity because it was steeper for the position versus time. Now our velocity versus time goes from a negative velocity and then jumps up to a positive velocity, and then for the rest of it's going to be 0. So the negative velocity is greater than the positive velocity, so the amount, we're talking about the speed there. So for the position versus time, we're going to have a steep slope in the negative direction, and we're going to start at 0. So negative slope, and then we have a positive slope, but we're still in a negative position because we moved in the negative direction. And then we have a 0 slope here for the last part. So this question right here says a student whose normal weight is 500 newtons stands on a scale in an elevator and records the scale reading as a function of time. The data are shown in the graph above. At time t equal to 0, the elevator is at a displacement of 0 meters and velocity of 0. So assume that the positive directions for displacement, velocity, and acceleration are all upward. So in looking at this graph, the first thing we want to do is we want to figure out the acceleration for 5-second time intervals. So the first part you see is 500 newtons, and we haven't really talked about force too much. So we're going to kind of just look at what's happening here. If we have a net force that's acting on him, then that means we have an upward force by the scale and a downward force of gravity. And if the scale's reading 500 newtons, then that means the net force is going to be 0. So we can use this equation right here, where the person's weight divided by gravity, that's going to give us the mass of the person, and then we take this to the other side, so we find acceleration. So the difference in force times gravity, which we're going to round to 10, and then divide by the weight of the person, and then that's going to tell us the acceleration. So you see for the first part, the force and the weight are both 500, so then the acceleration is going to be 0. The scale right here is going to say 700. So if we take the force, which is 700, minus his weight, which is 500, that gives us 200. We divide by 500, so 200 divided by 500 gives us 0.4, and then we multiply by 10, that gives us 4 meters per second squared. For this next part, of course, it's going to be 0 again because we're back to 500. And now we're at 300, so 300 is 200 below, so that's going to be negative 200 divided by 500, so it's negative 0.4 times 10, that gives us negative 4 meters per second squared. All right, so this part of the of this problem you probably wouldn't be able to do right now because we haven't talked about forces, but that is how we find the acceleration of each part. Now we're going to use this and find the acceleration versus time graph. Well, we said for the first 5 seconds it's going to be 0, for the next 5 seconds it's going to be 4, for the middle 5 seconds it's going to be 0, and then the last 5 seconds it's going to be negative 4. So that's what our acceleration versus time graph would look like. The next thing we want to do is we want to determine the velocity at each point. All right, so for the first point, we go from, we start at 0 velocity, and we have no acceleration, which means we're going to have 0 velocity at 5 seconds. So that brings us to this equation where final velocity equals initial velocity plus acceleration times time. We get 0 meters per second there. Now for the second part, we got an acceleration of 4 meters per second squared. So 4 times 5, so that gives us 20. 20 plus the initial velocity. Velocity here is 0, so 20 plus 0 gives me 20. And then we have this part right here where there's no acceleration, so that means we keep the same velocity of 20 meters per second. And then for this last part right here, we start with 20 meters per second, but we have an acceleration of negative 5 times 5, which gives us negative 20. So we end with 0 meters per second. So if we were to graph our velocity versus time graph, then we go from 0 to 20. So we got 0, then we come up to 20, and then we have 0 again, and we come down to back to 0, or I'm sorry, to 20. So 0 to 20 to 20, back to 0. And the slopes are going to be constant here because we got constant acceleration for each part. All right, so let's determine the displacement for each part. The displacement is going to be the area of a velocity versus time graph. So for the first section, we have 0 meters because we have 0 area. And then we're going to go up to this part right here, which gives us a triangle. So 1/2 base times height. The base is 5. The height is 20. So 5 times 20 gives me 100. And then half of that is going to be 50. Now for this section right here, we're looking for the displacement, the total displacement from the beginning. So we have to accumulate all of the area at every single point. So we got 10 to 15, so that gives us a base times height. The base is going to be 5, the height's going to be 20, so 5 times 20 gives me 100, plus this 50, that was this area right here. And then this area is also going to be 50, because base is going to be 5, the height's going to be 20, and then half of that gives me 50. So 50 plus 50 gives me 100, plus another 100 gives me a total of 200 meters for the total displacement of the elevator during the entire time. All right, so the displacement versus time graph, we start at 0, then we at 5 seconds we're still at 0, and then at 10 seconds we make our way up to 50. Now remember, we have a changing velocity, which means we have an acceleration, so it's going to be a parabola at this point. From 10 to 15 seconds we're still moving, which means we're still accumulating displacement, but we're moving at a constant speed, so we're going to get a constant slope for our position versus time. And then we are still accumulating positive area, which means we're still moving in the positive direction, but we're slowing down, so the slope of our position versus time graph will decrease until it's down to 0. So this is what our position versus time graph will look like, where we have 0 position, and then we have an acceleration, so it's a parabola, and then a constant velocity, and then our acceleration's negative for this point, get to 0 velocity with a 0 slope. This question comes from the 2000 Physics B question test for the free response. It says a velocity versus time graph for an object moving along the x-axis. So here we have our velocity versus time graph. So you can see what happens here. We're going to basically break this down and answer several questions about it. So the first question is indicate every time that the cart is at rest. Now when the cart is at rest, we have 0 velocity. Now it's tempting to say that this part right here is where it's at rest, or this part right here is where it's at rest, because it's a slope of 0. Which would be true if we're dealing with a position versus time graph. But since we're dealing with velocity versus time, then it's actually this point right here at 4 seconds and the position over here at 18 seconds, because those are where it crosses the x-axis. We have 0 velocity. The next part says indicate every time interval for which the speed of the cart is increasing. Now remember, increasing velocity doesn't necessarily mean that you have a positive acceleration. It means that acceleration and velocity are in the same direction. So if we look at the first part, we see that we have a positive velocity from 0 to 4 seconds because we're above the x-axis. But notice that's a negative slope. So a positive velocity with a negative slope, that means that we're actually going to be decreasing. We're getting closer to 0. But from 4 to 9 seconds, you see that we are moving away from 0. So the velocity is increasing in the negative direction. So being a negative velocity and a negative slope, then we have an increasing speed. For 9 to 12 seconds, we see that we have a positive slope, but we still have a negative velocity. So that means the velocity and acceleration are in opposite directions. Also from 17 to 18 seconds, we have a positive slope, but it's still a negative velocity. But from 18 to 20 seconds, we see that we have a positive slope, which means positive acceleration, and a positive velocity because we're above the x-axis. So that's going to be the two locations that we actually have an increasing speed, because the velocity and acceleration are in the same direction between 4 and 9 seconds, as well as from 18 to 20 seconds. And this part here says determine the horizontal position of the cart at 9 seconds. Okay, so from 0 to 9 seconds, we're going to have a displacement. If you remember, the displacement is going to be equal to the area of the velocity versus time graph. We have the initial position, so once we find the displacement, we can add that to the initial position to find our final position. All right, so from 0 to 4 seconds, we have an area of 1/2 base times height. The base is 4, the height is 0.8, so that gives us I think 3.2 when you multiply those together, but then it's half of that, so it gives you 1.6 meters for our actual displacement for that part. But going all the way to 9 seconds, we have to take this other area. Now the big mistake here is a lot of people just take this whole thing right here and make one big triangle out of it. The problem with that is that the area is between the x-axis and the line itself. So the x-axis and the line, which means we've got positive area here, but from 4 to 9 seconds, we have negative area. So the base here from 4 to 9 is 5. The height is -1, so that gives me -5, but then half of that gives me -2.5. So I got 1.6 plus -2.5, that gives me -0.9, but remember my initial position is 2, so that -0.9 plus 2 gives me 1.1 meters for my final position.